Hi, I'm Vikram. I'm going to be presenting my work on our work on LXDs, lightweight execution domains, a step towards isolation of kernel subsystems. Kernels are pervasive. They power millions of devices ranging from data centers to smartphones to autonomous cars. And they are the most complicated pieces of software. The de facto commodity kernel Linux has a huge code base with over 17 million lines of code and is developed at a rapid pace with over 70,000 commits a year, and is often written in unsafe programming languages like C and assembly. If you look at the Linux kernel, it has numerous subsystems, like 40 plus subsystems and 3,000 plus drivers. Due to these factors, a steady stream of errors are introduced into the kernel, which is corroborated by the Linux kernel CVEs reported over the years. And to be honest, these numbers are not real because there are numerous bug fixes that go into the kernel without having CVE numbers assigned. The situation is unlikely to change, and the numbers are not going to get down. Despite having a lot of tools in our defense arsenal, like the word cloud listed here, kernels remain vulnerable to attacks. Even advanced defenses such as code pointer integrity could be attacked by data-only attacks. Code pointer integrity seems to solve all the problem, like most classes of attacks, like code injection and control flow hijacking attacks. But with data attacks and automated tools for attack generation, these are vulnerable. So the attack scenario is real, and we need to do something to protect the security of the operating system. Why are kernels vulnerable? With a very few exceptions, historically kernels are monolithic, where the kernel and its subsystems such as networks, file system, and device driver all run in the same address space, where a vulnerability in a single component could potentially compromise the entire kernel. We need an isolation solution. Assume we can split apart the monolithic kernel into isolated components, as shown here. Here we have an example of isolating block driver and a network driver. In this scenario, say a bug appears in a network driver, and we can confine this within the isolated component and not propagate to the entire kernel. However, isolation brings in a lot of challenges. First, one can argue that I don't need to have an isolation solution for a monolithic kernel. I can very well run a microkernel. Sure, you can run it, but there is a huge amount of development effort that has gone into the monolithic kernel over years. We have 3,000 plus drivers. We have numerous matured subsystems. We should be able to reuse that code. So in order to run isolated domains with unmodified code, that is to reuse and support legacy code, we need to generate glue code. And the second challenge is that we need an environment to run our code under isolation. One can argue again that I can throw in a virtual machine and then everything is fine, but the overheads of virtual machine quickly makes the solution impractical. So we need a minimal environment to run code under isolated domains. And the next challenge is to cross the boundary, because though we run the code in isolation, it needs to talk to the rest of the kernel and should be able to call functions available in the kernel. So we need a low overhead mechanism to cross the boundary. Now I present lightweight execution domains, a framework geared towards addressing these challenges. Let's look at the challenges one by one. First, we are now convinced that we need to reuse the legacy code. And to reuse the legacy code, we need some form of glue code generation. How to generate glue code? Of course, you can go ahead and manually write glue code for a couple of drivers. But if you want to scale this process to hundreds of drivers, this quickly becomes infeasible, as you would be writing manual code for thousands of functions. So we need an automated way of generating glue code. To solve that, we created an interface definition language. The main goals are to decompose kernel code and to analyze the interaction patterns between the code that we wish to isolate and the rest of the kernel. We devise mechanisms that abstract the common interaction patterns of the isolated code and the kernel. For example, function pointers and shared data structures. Okay, so we have to explain the rationale behind creating a new IDL. Like, people would have already heard about IDL, and there are like hundreds of IDLs from protobuf to FIDL and Flick, etc. But why do we need to have a new IDL? Because all of those IDLs are geared towards general programming model, but here we are looking at a kernel programming model. Say a kernel often provides an interface like a dynamic registration interface where you could throw in a bunch of function pointers and register a subsystem or a driver. For example, here is how you register a network driver with the kernel. You provide a set of function pointers. I should thank the previous speaker for introducing you to NDO function pointer ops. Yeah, here we have NDO open, stop, and xmit, which are provided by the driver to register itself with the kernel. So we have an ops structure, and we assign that to a struct net device pointer and pass that to another domain. So these kind of complex interaction patterns cannot be uncovered by the existing IDLs. So we designed an IDL to create interaction, to understand interaction patterns in the kernel code. For example, the register net dev should cross the boundary if we wish to isolate a network driver. And this would be automatically translated to a remote procedure call in our IDL. Let's look at how the call is performed. Say we call register net device here, and this points to a data structure that is defined inside this domain. And we make a function call. We need to somehow let the other domain know about the data structure that we are referring to. One way is to share this data structure between these two domains, but this quickly breaks the isolation guarantees as a malicious driver running inside an isolated domain can override the pointers. So we need a mechanism to have shadow copies of data structures where each domain has its own private copy. And IDL seamlessly supports hierarchy of private objects. This brings into the natural question of, if you have two or more copies of data structures, how do you keep them in sync? We use a mechanism called projections to keep them synchronized. Here's an example again for the projection of struct net device. And projection contains a subset of members of the structure that needs to be marshaled across the domain to make a function call. And this is the projection that we define for calling register net dev. And we support directional attributes which specify the direction of the data flow. And allocation and deallocation of shadow copies of objects are supported using alloc-dealloc keyword. This is how an entire example looks like. It is represented as a module which specifies a kernel subsystem that we wish to isolate. And it contains a bunch of projections and RPCs. By feeding this IDL interface to an IDL compiler that we generated, we can automatically generate glue code, which would contain caller callee stubs for all the remote function calls that we wish to invoke. So we can generate glue code now, and we can call into other domains, but how to cross the boundary? We need to interact with the rest of the kernel, and we need to have a communication mechanism. That brings us to the choice of synchronous versus asynchronous IPC. In a synchronous setting, you can use page table isolation mechanisms to run the isolated code in a separate page table. But a traditional address space isolation would cost us 850 cycles of overhead. And this overhead is even without the meltdown mitigations. We assume that it would be fixed in the hardware. Instead of following a synchronous IPC model, we designed an asynchronous IPC where we run isolated driver and parts of the non-isolated driver in two different cores here, and then use cross-core IPC to communicate between these cores. This brings down the cost to 380 cycles for a call-reply invocation. This choice of asynchronous IPC brings in another challenge for us. An asynchronous IPC, as we have seen earlier, it works like a core sends a message to another core and then waits for a response from the other domain. And this causes the sender core to get blocked waiting for a response. So we burn CPU cycles. So we need a mechanism to utilize those cycles effectively. We created lightweight asynchronous runtime This is similar to core routines, where we create threads of execution and context switch between those lightweight threads. Sure, where we can put this to use. A typical example would be in a packet transmission loop. Assume we wanted to send a bunch of packets, and you do it using a while loop. And instead of calling a real function to cross the domain, we wrap it around with an asynchronous macro, which converts that into an asynchronous thread. And the execution starts by sending the first packet, and assume that gets blocked waiting for a response from another domain. Our runtime automatically switches the execution to the next line after the async thread, and then continues to transmit the next packet. Having solved all these challenges, let's evaluate our framework on two flavors of device drivers. The first, software-only device drivers. These device drivers represent a device with infinite bandwidth and is not associated with any hardware. And this helps us to understand the overheads of isolation better. For example, a dummy network driver or a null block driver. We evaluate our infrastructure. We evaluate our experiments on MLab infrastructure. Typically, we run our experiments on a 4-socket, 32-core Xeon server. We evaluated dummy network driver by running iperf benchmarks. We measured the transmission I/O operations per second. We varied the number of application threads from 1 to 27. To accommodate these many application threads, we also varied the number of LXD threads from 1 to 4, where each LXD thread occupies a core in a NUMA node, as shown here. And the application threads are distributed across the other CPUs available in a NUMA node. And each application thread is pinned to a particular CPU and communicates only within the LCD of that NUMA node to avoid cross-NUMA overhead. This is how the entire setting looks like for a 27-thread scenario. And this is the performance benchmark for null-net device driver with native and isolated driver. In a single-threaded LXD case, our native achieves 956K I/O operations per second, whereas our isolated driver achieves 730K I/O operations per second, which is 76% of the performance of the native driver. And we pay an isolation overhead of 710 cycles per packet. In a multi-threaded setting, our isolated driver achieves 70% of the performance of the native driver by running 27 application threads. The second flavor of device drivers, we isolated drivers that are backed up by real hardware. Specifically, we decomposed a 10 Gbps Ethernet driver with Intel 82599 hardware. And we ran iperf benchmarks and measured the packet transmission bandwidth. And if you look at the TX bandwidth, in a single-threaded case, isolated is 12% faster. The benefit it gets is from burning one more additional core in the asynchronous IPC setting. But this quickly disappears as we add more number of application threads. For 2 to 6 application threads, we are within 6 to 13% of the performance of the native driver. And in the reception bandwidth benchmark, our single-threaded case, isolated driver performs on par with the native. This is due to burning one more additional core and the fact that we do polling in a different way. In a native driver, the packet reception is handled by an interrupt and then offloaded to a soft IRQ thread, and this incurs a context switching overhead. Whereas in our isolated setting, we use busy polling to reap the packets from the hardware. And for 2 to 6 application threads, we are within 12 to 18% of the performance of the native driver. And these are the drivers that we isolated to evaluate our framework. And there are some of the limitations of the framework. First, we burn more cores because we use an asynchronous IPC design, and asynchronous execution model brings in a lot of challenges. For example, it's hard to decompose an interrupt-related path or data structures involving lock. And manual generation of IDL is hard. For example, if you want to isolate complicated USB driver or a network driver, you would be looking at hundreds of functions and analyzing those manually. In the future, we wish to explore a low overhead alternative synchronous isolation mechanisms such as VMFunc or MPX. And we also would like to explore an auto generation mechanism for IDL using static analysis. In summary, we created lightweight execution domains, which provides general abstractions and mechanisms for isolating device drivers, and we evaluate our framework on device drivers, and we demonstrated that isolating device drivers is feasible with minimal overhead. This concludes my talk, and I'll be happy to have any questions.
Hey, Russ Blaine from Apple. Very interesting talk and great work. This really reminds me of something that we are about to ship with the next version of macOS and iOS that's coming out in the fall. We moved a bunch of device drivers into userland. I'm just wondering why, or if you considered going one step further in your isolation domains and just running them in user mode as standard processes or daemons. And you get a lot of benefits from having them fall into the user abstraction that way. You can utilize existing communication mechanisms between the kernel and userland instead of having to invent new IPC mechanisms.
Yeah, that's a very interesting thought. The problem with putting everything to the user space is that like you need some parts of the code still to be remained in the kernel, right? So you need to pay a performance price of like upcalling to the kernel or sending something to the kernel. Like for example, a previous work called microdrivers. Microdrivers worked on this approach, and I think you need to manually rewrite the code. And one of the important goals of our project is to not rewrite the code. I mean, like we should be able to use legacy code as is.
Very interesting talk. So do you need to burn a core for every driver? Or all the drivers that are in different protection domains, all of them are going to be executed in the same LXD core?
Yep, that's a very good observation. The thing is that, like, say for example, if we are isolating like many drivers, go ahead and isolate many drivers, and then some can be classified as non-performant drivers. Say for example, like just very simple I2C driver, which does not have a huge performance overhead. Which will not have any problems with having an overhead. And there are some drivers which are performant, like network driver, a 10 Gbps Ethernet driver, or a block driver. And for that, we have to burn additional cores in order to bring in the performance benefits. And for other drivers, we can put together in like just one core, and then say like all the instructions go through that.
Okay. So another question, because nobody else is waiting to ask question. So burning a single core for your network, you're basically, you're going to get as much as a single core can give you, as opposed to like regular monolithic kernel. When you run like with 10 threads, you get 10 times, you can basically get 10 times processing, and you get more TCP packet processing out of the network, especially with multi-queue network. So do you think this is a limitation? And if so, is there a way to fix it?
Yeah, good question. So this is the inherent limitation of running an asynchronous IPC mechanism, right? So that's why we would like to explore a synchronous IPC design where we don't need to burn any more cores. So we can synchronously context switch into that domain and then perform all the operations.
Okay, thank you.
Thank you.
All right, I'm actually going to steal a moment for a question. So in our work on enforcing memory safety on the Linux kernel, we noticed that there were buffer overflows and other sorts of bugs in components other than device drivers, such as the networking stack and the socket layer. Do you think your approach could actually be extended to encompass larger kernel components like the TCP IP stack or other various of the pluggable components that are not part of the quote-unquote core kernel?
Yep, that's a very interesting and thought-provoking question. So we got similar set of questions from the reviewers as well. The thing is that like the isolation of a monolithic kernel has its own downsides. Like there are limitations to which components you could decompose. For example, you cannot do a virtual management layer, virtual memory management, or you cannot do a block layer because the interaction patterns are huge and it's like tightly coupled with the rest of the kernel. Like you can call like a socket interface from the user space, and that that also calls like the protocol send message. So there are like two ends to it, and it's really hard to come up with like clean slate mechanism to isolate these components. But if we want such kind of isolation, like really isolating subsystems, then we should be looking at some clean slate approaches where the components are not so tightly coupled.
Okay, thank you.
So I have a question. I think you gave some numbers about the cost of switching domains and like if you are on the same CPU and everything. But I was wondering, because you are doing cross CPU now, will the overhead of changing the domain in a cross CPU design like this one change depending on the coherence traffic and so forth, so on?
Sorry, I
So
missed
you're
the later
giving-
part of your question.
Yeah, I'm saying the 380 cycles that you are saying there now. Is it under any potential coherence traffic?
The asynchronous IPC works on top of the cache coherence protocol.
Right, but I mean, if you have a lot of misses, will that be the same?
You mean like if you stress
Yeah,
the cache domain?
yeah.
We haven't really stress test the cache domain to create a lot of misses or conflicts.
So it could be even more than the 8050, let's say.
Yeah, I mean like, which means like either the system is heavily loaded or it is under some attack, right?
Right, but it could be
So-
heavily.
Yeah, it could be heavily loaded, very well, yeah. No, we didn't measure it, actually.
Thanks.
Thank you.
Let's thank our speaker.